All right, so we were implementing a stack in the last class. This time our implementation is going to use a linked sequence of nodes as opposed to an array. You can implement a stack using an array as well, but we're going to use a linked sequence of nodes. Similarly, you can implement a list or a queue or any other linear data structure using a linked sequence of nodes, right? Or an array. They all work, right? They all have the biggest difference between the two implementations in terms of computational complexity is that anytime you add something to a linked sequence, it's potentially in O1, whereas when you add something to an array-based sequence, it's potentially in ON, right? Because in an array-based sequence, you might have to resize the array. In a linked sequence, all you have to do in many cases is create a new node to hold the new element and then insert the element into the structure somehow. So for our stack, we need a pointer. So top's going to be a pointer to the top node, right? And our nodes are going to be these things that thing drawn there, right? So our node is going to have storage for an element, and it's going to have another pointer that points to the next node in the sequence. Right? So if we push another element onto the stack, oh wait, sorry, there's your link. Right, so when you push an element onto the stack, all you're going to do is you're going to make a new node, right? So allocate space for a new node using malloc, right? Set the element in the node, right? Adjust the node's link so that it points at the current top node, right? And then adjust the top pointer so that it points at the new top element. Right? When you pop an element off the stack, right? So if I want to remove that 3 off the stack, I need to remember what the value of the 3 is because we want to return that to the caller. I want to adjust top so that it points at the next node in the sequence, right? Now we can get to the next node in the sequence, right? Because all we have to do is follow top to get to the current top node and then follow that node's next pointer to get to the next node. Right? So we can get to that node pretty easily and you can adjust top. Right? And then we're going to remove this node. Now when we remove this node, we're going to free the memory that was allocated when we created the node. Right? So when that node disappears, there's going to be a call to free to deallocate the memory. And then you adjust the size of the stack. All right, so let's take a look at the source code for this thing. So as always, you start out with a header file. Right? And so our structure is going to be called lstack for a linked stack. So we're going to start out with a header file. We have an include guard up here. Right? There's our type def. So we're going to use, just like with the list, we're going to use an opaque type here. Right? So I'm going to declare a structure called lstack. Right? I'm going to create a type def so that I can just write lstack instead of struct lstack everywhere. But I'm not going to define the structure here. Right? So I'm going to define the structure in the source code file, lstack.c. Right? We're going to have a function that allocates a new stack and returns a pointer to the allocated stack. Right? We're going to have a function that takes in a pointer to a stack and determines whether or not the stack is empty. Another function that takes in a stack and then returns what, the size or the number of elements in the stack. And then, of course, there's push and pop. Right? So push pushes that int element onto the stack S, and pop removes the top element off in the stack S. There's a function to print the stack, and then there is a function to free the stack. Now, freeing the stack for a linked list is going to be a little bit more complicated than for an array-based structure. So we'll see that shortly. Okay, so in our source code file, we're going to declare the node structure here. Right? Notice that anybody that's using lstack, they only have typically they'll only have the header file. Right? And notice that in the header file, there's no mention of a node anywhere. Right? So the public interface or the visible interface of the data structure doesn't make mentions of nodes anywhere. So there's no way for the caller to know that this is actually a linked stack. Right? It could be some other implementation of the stack, like an array, for example. If you're going to implement a linked stack, though, you have to create a structure for the node. Right? So again, we're going to create a node called struct called node. I'm going to make a type def named node, so I can just write node instead of struct node everywhere. right? What's inside of a node? Well, if we're going to store ints in the stack, then we can just create. Then our space for the our member for the element is just an int variable. Right? Now remember, we need a pointer to the next node in the sequence. So I need a pointer, right, to a node. Oh, sorry. I need a pointer to a node, and we're going to call it next. Right? If you remember CISC 124, this is exactly the same as the node class. Right? You'd have an element here, and then you'd have a reference to the next node. Right? Instead of a reference, we have a pointer in C. Okay, finally, we can describe our stack structure. Right? In our stack structure, all there is a pointer to the top node. Right? And there is the number of elements in the stack. Right? You technically don't need this member here, but it's convenient to have. Right? If you don't have the member here, then whenever somebody wants the size of the stack, they have to iterate over the sequence of nodes and count the number of nodes in the stack, right? Which we want to avoid. So we're gonna keep a variable that keeps track of the size of the stack. Okay, so to allocate the stack, right? So our init function, right? What are we gonna do? We're gonna allocate memory for the stack structure. So there's a call to malloc. Right? How much memory do we need? Well, we need enough memory to hold one of these L stack structures. Right? Notice the comment in green, right? So the comment in green makes doesn't allocate memory for a stack. Instead, what it does is it makes a little local stack variable. Right? So you can write this. It will compile. Right? So in other words, you can just make a structure variable called t, right? Set its top node to null, set its size to 0, right? If you try to return the address of t, that's going to fail when someone tries to use the stack, right? Because this structure tier, the variable t has automatic storage, right? Its lifetime is the lifetime of the function, right? If you return if you return the address of that variable, the variable doesn't exist when the function returns. And so the caller does not have a valid stack, right? You have to use dynamic memory allocation here. Right. Once you've allocated the stack, you can go ahead and set its members here, right? So you set the top pointer to null, indicating there are no elements in the stack, and you set the size to 0, right? And then don't forget to return the stack S. Right. The other functions are all going to be exactly the same, or more or less. Sorry, like is empty and size, they'll be exactly the same as those functions are in the list class the list structure that we implemented. Right? So is the stack empty? Well, just look at the size of the stack. Right? Is it 0? Return true. If it's not, return false. Right? To get the size of the stack, you just return s arrow size. Right? And remember, the arrow operator is the pointer, dereference, and then member access operator. Okay, so the only interesting functions here are push and pop. Well, push, pop, and free. Right? And they're not even that interesting. So push, you just follow the slide, right? Where is the slide? Here. Right, so for push, if you follow this slide, you literally implement steps 1, 2, 3, and 4. Right? So make a new node to hold the element pushed onto the stack. Okay, so to make a new node, oh, I just closed it, didn't it? Yes, I did. Sorry. Sorry about that. Okay, so to make a new node, right, it's just to call the malloc, right? Right, so allocate a new node. Right. Step 2, set the link of the new node to point to the current top node. Right. So, and next. Right. So the next, so the new node, we're going to set its next pointer so that it refers to the current top element of the stack. Right. So and next is just equal to s top. Right. Assign the element to the node, or to the member element in the node, right? So any lem is equal to elem, right? Step 3, I think, is set top to refer to the new node. Right? So set top to refer to the new node. Right? Update the size, and then return true to indicate that we successfully pushed an element onto the stack. Again, if you remember CISC 124, it's almost the exact same code, right? Instead of malloc, you call new, right? Make a new node, right? Instead of the arrow operator, you just use the dot operator. Right? Pop is similar to, again, pop, you just follow the slide, right? So to pop an element from the stack, you're just going to, right? Implement those steps there, right? So we're going to remember what the element is that's stored in the node. We're going to set the we're going to set the pointer to point to the next element deeper in the stack. Subtract 1 from the stack, from the size of the stack. Right? I'll come back to the assert in just a second. Right? So I'm going to get a reference to the top node. Right? There's something that's you have to remember here when you pop the top node from the stack. Right? So I'm going to remember what the current top node is, because I'm going to adjust top in just a second. Right? So remember what the current element is at the top. Right? Adjust the current top pointer so that it points at the next node in the sequence. Right? So remember the top pointer is just S top. Right? The next node in the sequence is whatever the current top points at. Right? So, sorry, what the current top node, what its next pointer points at. Right? So S top is equal to top next. Decrease the size of the stack by 1. Now, what you have to remember here is that in push, you allocated space or memory for the node. Right? And so when you pop the element from the stack, you have to deallocate that memory, right? Because we're done with the node now. Right? We've removed the top element from the stack, so there's no reason to keep the top, there's no reason to keep that node around. So you have to remember to free the old top node. Right? And once you've done that, you can return the element here. Okay. Any questions so far? All right. Print, I'm just going to ignore for now. Well, let's do print, I guess. I guess this is useful for the 120 for people who are currently taking 124. So to print a stack, you have to follow the sequence of nodes, right? And so we haven't gotten there in CISC 124 this term yet. And so often when you work with these linked structures, if you want to iterate over the elements of the structure, what you need to do is you need to follow the sequence of nodes, right? Because you don't have an array in this case. Right? And so the general pattern for this is you get a pointer to the current top node, right? And then you write a little while loop, right? So while n is not null, then you know that there's another element in the stack to process, right? Inside the loop, so this is print, so we're just going to print the element, right? So we're going to print the element using printf, right? And now you need to adjust n so that it goes to the next node in the sequence. Right? And the way you adjust n is you just write n equals n dot next, or in this case, n arrow next. Right? That moves n to point at the next node in the sequence. Right? If there's another node in the sequence, so if it's not null, then the next time the while loop runs, n's not null, so the while loop, it runs. Right? Adjust n again. Right? Eventually, you'll get to the last node in the sequence. Right? And then when you adjust n again, right, n dot next will be null. Right? Because the last node in the sequence has no next node, right? And then the while loop stops running, right? And so print is an example of print is an example of a function that iterates over the sequence of nodes, right? Anytime you need to iterate over the sequence of nodes, it's always the same pattern, right? Get a reference to the starting node, right? While that node is not null, do something, and then inside the loop, adjust the pointer to that node. Okay, finally in free, so free, again, you have to remember that if you have a stack that actually has some elements in it, when you free the stack, you have to free all the nodes that you allocated back in push, right? So remember, push is the only way to add elements to the stack, right? When you remove the stack from memory, you have to remove the nodes as well. Right? So how do you remove the nodes? Well, I have to iterate over the sequence of nodes. Okay, so we're going to start at the top of the stack, right? So while n is not null, right? Now, the order that you do things here is important, right? So the first thing I do inside the loop is not free n, right? So remember, n's pointing at one of the nodes. I'd like to get rid of this node, right? I can't free n here because I need to somehow get to the node after n, right? If I free n at this point, I can no longer get the next element from n, right? So the very first thing I do is remember what is the next node after n, right? Once I've remembered that, I can go ahead and free n, right? And then set n to equal next, right? So the order here is important, right? If you free n first, then line 77 is no longer valid, right? Because as soon as you free n, you can't dereference the pointer n, right? Which you need to do to get to the next node, right? Again, the pattern is exactly the same as in print, right? You start out at the node where you want to start the iteration at, right? While that node is not null, right? The last thing you do is update that node. Once you've freed all of the nodes, you can finally free the memory for the structure itself. So now you can free S here at the end, right? And that's it. So stack's pretty straightforward to implement, right? You can do a queue in exactly the same way, right? So for a queue, you would implement NQ and DQ, right? The methods change slightly, but all of the ideas are exactly the same, right? In NQ, you would allocate space for a node, right? In DQ, you would have to free the memory associated with the node, right? And that's it for a stack. So stacks usually considered the easiest linear data structure to implement, right? Either whether you're using an array or a linked list, it's pretty straightforward in both cases, right? All right, any questions about a linked stack? Okay, so then the big disadvantage of the data structures we've implemented so far is that they assume something about the element type, right? For the stack and the list, we both have sequences that can only hold ints, right? If you want to implement a list or a stack that holds something else, right? Your first alternative is to basically copy all of this code, right? And then change the element type for the node, and then give your new data type a different name, right? So if you wanted a string stack, you might call it S stack or a string stack or something like that, right? Instead of having an element that's an int, you would have a pointer to a car, right? If you wanted a double stack, right? Copy all the code, call it something like D stack or double stack, right? Instead of an int element, you would now have a double element, right? The rest of the code is almost all the same. So let's take a look at that, right? So that's the way you want to avoid, you don't want to implement it that way if you can help it, right? And so this is the question of genericity, right? How do I make one data structure that can hold any element type, right? And you know in Java, well, many of you know in Java, that you can use Java's generic facility to create such a data structure, right? C doesn't have that particular mechanism built into it, right? So if you wanted to make a new collection of something, right, you end up making, one way is to make, is basically to copy all of your code and adjust it so that it can hold the new data structure, the new type, right? So this involves a lot of manual copying and code duplication, right? When you actually look at the code, it's going to be almost all exactly the same. So C++, so that's a language that you can think of as being an object-oriented version of C. It actually does this manual copying and code duplication, right? So through this process, through this mechanism called templates, right? So C++ templates is the C++ mechanism for creating a generic data structure. The compiler does all of the copying, code duplication, and swapping of types for you, right? So at least the compiler does the work for you, right? C++ templates are actually more sophisticated than this. They have a lot of other features. I think eventually you'll learn the language a little bit anyway in undergrad if you continue with computing science, right? Java generics is a completely different mechanism for creating generic types, right? And so in Java generics, basically the compiler reads your code, makes sure you're using the generic structures correctly, and then tosses away the element type, right? It literally discards the element type. So when you make a list of integer, if you actually look at the code that's generated, the list never knows it's actually a list of integer, which is kind of surprising, right? So when you make a list of string, for example, at runtime, it's actually a list of object in Java, right? All right, so how do we do this in C? So there's no generic type mechanism. So there's no templates, there's no generics, right? All that we have is this pointer to void, right? So remember, a pointer to void can point at anything, right? And so it looks like that's going to be our solution here, right? So if I want to make a stack or a list that can hold elements of any type, right? Rather than holding the elements directly, we're going to be holding pointers to the elements, right? And I can use a void pointer to represent that, because a void pointer is allowed to point at anything. Right. Now, when you do this, it's not the same as a Java collection anymore, a Java generic collection. Right. So remember, in Java, if you make a list of string, it can only hold strings. Right. So instead, what this is going to end up looking like, it's going to end up looking like a Python collection. Right. Because we're going to be holding pointers to elements, and the pointers are going to be void pointers. Right. The caller or the user is able to put any element type into our collection, right? So that's exactly like what happens in Python, right? Similarly to what happens in Python, there's no built-in type safety, right? So if I make a list and I add an int, then a string, and then a double to the list, right? It's up to the programmer to remember they added an int, then a string, then a double into the list, right? There's no way for our data structure to remember what are the precise types that are in the collection, right? And so now there's a lot of responsibility shifted onto the programmer to make sure that they're using this collection correctly. Okay, so implementing this thing is actually surprisingly easy, right? So our node, that's our structure that holds the elements, right? So remember, we had int elem here, right? Now our elements are just going to be pointers. Right? So it's going to be a pointer to an element, right? The pointer type is void, so that we can point at any object. Next state is the exact same. All right, so if we look at the implementation of stack, right, you're going to see that there's three functions that don't have to change at all. Right? So if we go to, where is it, stack? Right? So you look in init and you ask yourself, right? So remember, node's going to change, right? So you look in init and you ask yourself, does node show up anywhere? And the answer is no, it doesn't show up anywhere. Right? So lstack init is exactly the same whether or not we're implementing a generic stack. Right? What about isEmpty? Well, isEmpty only looks at size. So again, this doesn't change. Right? And size? Well, size only looks at size, so this doesn't change either. It looks like push is going to have to change because we actually need to use node here. Right? So push is going to change because we're no longer pushing int elements onto the stack, right? We're going to be pushing whatever the user wants onto the stack. Right? So push and pop, they change only very slightly though, right? So instead of pushing an int element onto the stack, we're going to be pushing a pointer to some element onto the stack, right? And instead of popping an int off the stack, we're going to be popping a pointer to an element off the stack, right? The code, there's almost no changes to the code, right? You change the parameter type and you change the return type, and everything else is exactly the same, right? It's only when you get to print and free that you realize that there's a problem, right? So when you look inside print, right, there's a line that says printf %d, right? Because it's going to print an element, it's going to print an int element, right? If someone's making a stack of something else, that's not going to work anymore, right? Furthermore, our data structure has no idea what the element type is, right? So remember, all it gets is a pointer to, is a void pointer. So it has no idea what element types are in the stack, right? And so what that means is, inside print, we have no idea how to print that element, right? Who does know how to print the element? Well, the caller knows how to print the element, right? So somehow we need a mechanism that lets the caller communicate how should we print an element, When you look at free, there's another problem. Well, so when you look at free, it doesn't look like there's a problem, right? It turns out there actually is, right? So when you look at free, you say, well, no, this ought to work, right? So it doesn't matter what's in the stack, right? I'm going to free each node, right? And then I'm going to free the stack data structure. This doesn't look like there's any problems, right? The problem that you run into here is that if you free the sequence of nodes, right, but you don't free the elements that are referred to in the nodes, right, you potentially end up having a memory leak, right? Because there's no way for the caller, the caller does not necessarily still have pointers to their elements anymore, right? When you delete all the nodes, now no one has a reference to those elements anymore. So there's no way to free the elements from memory. So if the caller wants the stack to deallocate memory for the elements when it deallocates memory for the nodes, right, you somehow have to free the element here, right? The problem that you have here is that you don't know how to deallocate the memory allocated to that element, right? If the caller has a very, or even a slightly sophisticated element here, right? So imagine they have a structure of some kind, right? So you make a stack and they've pushed a bunch of pointers to structures onto the stack, right? When you free the memory allocated to that structure, you might have to do some extra work, right? Just like we had to in list, right? So in the list, we had to free the array, right? If you have a stack of stacks, you've now got to free the sequence of nodes in the stack elements themselves, right? But we don't know how to do that because we don't know how these structures are made, right? All that the stack has is this pointer to void. So you don't know how to do that either. Who does know how to do that? Well, the caller knows how to do that. So again, it looks like we need some way for the caller to communicate how should you do these things, right? So printing or freeing an element, you can describe that with an algorithm of some kind, right? It's a function of some kind, or possibly a sequence of functions, right? The user knows how to do this, right? So in C, all algorithms are implemented either as functions or sequence of functions, right? And so what we really want is for the caller to somehow be able to tell us, hey, what function should I use to print an element? Or what function should I use to free an element? Right? And so the solution in C is to create what's called a pointer to a function. Right? So every function has a type in C. Right? Okay, so suppose you have, in general, a function has a return type. Right? It has a name, and then it has a comma-separated list of parameters. Right? So return type, name, parameters. If you want to create a function, if you want to create a pointer to a function of this type, right, then the way you create the pointer is as follows. Right? The syntax is really awful, right? So you copy all of this, right? So copy the return type, copy the parameters, right? Copy the return type, copy the parameters, right? Change the function name to round brackets, right? And replace the function name with the pointer name that you want instead. So this is your this is your pointer variable name right here, right? And then slap a star in front to indicate that's a pointer, right? So one more time. Here, here's your function, right? Copy the function, right? So copy the return type, copy the parameters, right? Return type, parameters. Replace the function name with the name of your pointer with a star in front. Right, so what does this look like? I guess we're going to look at pointer to, pointer to func. Uh-oh. Oh, there it is. Okay, so inside pointer to func, we've got a bunch of simple functions, right? So we've got a function returns void, right? It's called do nothing, right? Has no parameters, right? It does nothing. It just returns, right? Here's a function that returns void, right? It's called print int, and takes in one int value, right? Prints the int, right? So if someone was making a stack that can hold, and they wanted to push a bunch of int values onto the stack, right? When you go to print the stack, right? Our stack needs a function that might look something like this, right? It needs to know how to print an int, right? Here's max, so it returns the int that is the maximum value of A or B, right? So returns one int, takes in two ints, right? Here's min, right? Notice that min and max, right? Their return types are the same, right? Their parameter lists, their types are all the same. The names don't matter in the parameter lists, right? So this is returns an int, takes two ints as inputs, right? So if I make a pointer that points at max, I can reassign that pointer so that it also points at min, because they have the same, their pointer to, the pointer to function types are exactly the same, right? Returns an int, has two ints as inputs, right? Returns an int, has two ints as inputs, right? So I can create a pointer to either one of the, I can create a pointer and assign either one of these functions to the pointer. Right? Here's a pointer that returns a double and takes in a double, right? Here's a pointer that returns an int, takes in two ints, and now there's our, that's our pointer to a function, right? So the way you read this is, right, fp is a pointer to a function that returns an int and has two ints as inputs, right? So in other words, for fp, I could pass in a pointer to max or min, right? Because both of these functions return an int and have two ints as inputs, right? So one more time, fp is a pointer, right? So star fp, you know it's a pointer, right? It's a pointer to a function. It returns that returns an int and has two ints as inputs, right? Finally, there's another function that also does nothing, right? So returns void and has no parameters, right? Okay, so I would like a pointer to either do nothing or also nothing, right? Returns void, has void as its parameter list, right? So if I'd like to create a pointer to that function, copy the return type goes here. Copy the argument list types, that goes there, right? In round brackets, write star, and then give your pointer a name, right? So in this case, it's ptr1. So ptr1 is a pointer to a function that returns nothing, has no arguments, right? You can assign that function, you can assign that pointer any function that matches that return type and matches that parameter list, right? So I can say it's equal to do nothing, right? So pointer 1 is now a pointer to do nothing. If you want to, you can write the address of as well in front, right? So you're allowed to write address of do nothing, or you can just write do nothing, right? Both are acceptable in C, right? Notice that I can assign any function to ptr1 as long as that function has no return to value and has no arguments, right? So I can assign also nothing to ptr1, right? And now hopefully you can see what's going to happen here, right? So you can make this pointer, you can make a pointer to a function point at any function as long as that function has the correct return type and the correct argument list, right? And so in our stack data structure, when in the print function, we're going to ask the caller for a function that returns nothing, takes in a pointer to void, and it knows how to print the element that's being pointed at, right? Okay, what about print int? So go back to print int, right? Returns void, its parameter is type int. If I wanted to make a pointer to that function, right, copy the void, the return type, copy the types in the parameter list, right? In round brackets, write star and give it a name. So ptr2, is a pointer to a function that returns nothing, has one int parameter, right? And I can make that point at print int, or any other function that returns nothing and has one int as its argument. Right? For max, right? Remember max returns an int, takes in two ints, right? So ptr3 is a pointer to a function that returns an int, has two int parameters. Right? So I can make that point at max, or I can make it point at min, either one. Right? Make double. So make double returns a pointer to double, has one double parameter. Right? So copy the double star and the double. Right? So there's your double star. Right? There's your double. Right? Give your pointer a name. So it's ptr4, right star, and the round brackets. Right? So ptr4 is a pointer to a function where the function returns a pointer to double and takes in a double as an argument. Right? Again, you can write address of make double or just make double. They're both fine. Right? And nothing changes even if your function has a more complicated signature like this. Right? So remember, make int, right, looks pretty gruesome, right, when you see it the first time. Right? You just take it apart one piece at a time. Right? So it returns a pointer to int. Right? Has two int parameters. And its third parameter, right, is a pointer to a function that returns an int and has two ints as inputs. Right? If I want a pointer to make int, right, just copy everything. Right? So I'm going to copy all that. That all goes to here. Right? Change the name of the function so it's got round bracket star and give it a name. Right? So ptr5 is a pointer to a function that returns a pointer to int, has two int arguments, and then finally a pointer to some function. Right? Okay, so when you so once you've got a pointer to a function, you can then call the function via the pointer. Right? So sorry, ptr5 is my pointer. Right? If I want to call the function that ptr5 is pointing at, right, dereference the pointer. Right? That gives you a function. Right? Function needs some arguments, so round bracket, right? It needs an int and an int, right? So 5 and 10 in this case. And it needs a pointer to a function that returns an int and has two ints as arguments, right? So I've got one of those up here, right? ptr3 in this case is a pointer to min at this point, right? And so I can pass in ptr3 as the pointer, right? Make int is going to return a new int, right? That is ptr3 is min, so it's the min of 5 and 10, right? So x is going to be pointing at an int whose value is 5 in this case, right? If you change ptr3 so that it points at max, right, then make int is going to make an int that is the max of 5 and 10, right? Because ptr3 is a pointer to max, right? And when you look at make int, what does it do? It calls the function, passing in your two arguments a and b, right? So if that's max, then it's going to give you the max of a and b. If fp is pointing at min, it's going to give you the min of a and b. Right? When you call the function, you don't have to dereference the pointer. Right? So you could write just ptr5 and now 1, 3, and ptr3 in this case. Right? So you can, if you want to, dereference the pointer, right? But because it's a pointer to a function, you can just use the pointer name as an alias for the function itself. Right? The language will automatically dereference the pointer for you, and then call the function. Right? So you don't have to take the address of a function when you assign it to a pointer. you don't have to dereference the pointer to call the function, right? You just use the pointer name in place of the function name, right? So now that you've got pointers to functions, this becomes a very powerful thing that you can use in a C program. Oh, sorry, any questions about any of that? Conceptually, it's not difficult to deal with. Well, it's not too difficult to deal with. The hard part about all this is getting used to the syntax, right? The pointer to a function syntax is kind of gross, right? Once you get used to the syntax, it's not too difficult to use, right? But you do have to get used to the syntax. Okay, any questions? Because we're going to start to use this now in our stack implementation. All right. So remember in our stack implementation, everything is a pointer to void, right? We've got pointers to elements. We don't know what the element types are, so they have to be pointers to void. If I want the stack to print an element, right, it needs a function that can print an element that's pointed at by a void pointer, right? So inside of our print function, I want to call something like print elem that takes in a pointer to an element, right? Where the element type is unknown, right? It's, well, unknown to the stack, right? So it needs a pointer to void star here, right? It's const because we're not going to change, print does not need to change elem, right? So if I want a function that looks like this, right, then the caller can specify such a function by giving me a pointer to a function that looks like that, right? So in other words, they need to give us a pointer that returns void, right, and has const void star as its argument, right? So I want a pointer PTR to a function that returns void and takes in a const void star element, right? Okay, now look, this is kind of gruesome to read, right? Actually, this isn't so bad, but when you have much more complicated functions, it starts to become really awful to read, right? So instead of requiring the user to deal with the pointer to a function syntax, right, this is the appropriate time to use a typedef, right? So, right, void something, some pointer name, right, const void star, right? So void const void star, right? Print elem func, that's the typedef name, right? So that's your tag name now, right? So this typedef says that print elem func is just an alias for a pointer to a function that returns void and has const void star as its parameter, right? So again, notice that the normally in a typedef, the typedef tag goes here, right? But when you have a pointer to a function typedef, the name goes inside the round brackets after the star, right? So what would normally go there now goes inside the round brackets, right? So one more time, print elem func, that's the name, that's just an alias for the type void pointer to function const void star here. Right? So if I put this typedef in my header file, right, then all someone needs to do to specify a function that can print one of their elements is write print elem func, some variable name, give me a pointer to that function. Right? For free, it's the exact same thing, right? So for free, I want to free an element pointed at by a void pointer, right? Notice this isn't const because we have to actually deallocate the element, right? So you're actually going to modify what element points at, right? Returns nothing. So I want a pointer to a function that returns void, has void star as its argument, right? Again, I can make a typedef to that function, right? So just copy all of this, stick it up here, right? Your typedef name goes there, right? So instead of the pointer variable name, it's now the typedef name, right? So this says free elem func is just another name for a function that returns void and has void star as its input, right? And now you're ready to finish off the stack implementation. Right? Is it here? Okay, so okay, so this is stack.h. It's our generic stack implementation, right? It's going to be exactly the same as lstack.h, right? Except we've now got a type def to a pointer to a function that prints an element, right? So print elemfunc is just a pointer, is the name that the user can use to make a variable that points at a function that returns void and has const void star as its argument. Right? Free elemfunc is just the name that the user can use to create a pointer variable that returns void and has void star as its input. Right? Everything else is the same, except for push and pop. Right? Push now takes in a pointer to an element. Pop now returns a pointer to an element here. Right? Print is almost the same, except now we have to let the caller specify what function are we going to use to print the element. Right? So notice, instead of writing that awful pointer type, I can just write print elemfunc here. Right? And then give it a name. Right? So print elem is a pointer to a function that can print an element. Right? For free, right, the caller has to pass in a function that knows how to free an element. Right? Now notice here that it could be the case that the caller does not want us to deallocate the elements that the stack is holding, does not want us to deallocate the elements that the stack has pointers to. Right? Because the caller might have those, references to those elements themselves, right? And so they're going to free them later on themselves, right? So here, if you pass in null for this function, then stack free will not try to deallocate the elements. Oops, sorry. Okay, so what changes inside of the stack implementation? Almost nothing changes. Right? Init doesn't change because it never needs to access a node. Right? Is empty and size don't change because they never have to access a node. What about push? So push has an element here now as its input. So this is going to change a little bit, look maybe. Right? So let's see what happens. Right? So allocate memory for a node. That's the same as before. Right? Set the next link of the node so that it points at the current top of the stack. Well, that's the same as before. Right? Set the element in the node to elem. That's the same as before. Right? Adjust top so that it points to the new node. Same as before. Adjust the size of the stack. Same as before. Push doesn't change except for that line there. Right? Pop's exactly the same. Nothing changes except for the return type. Right? Instead of returning an int, you're now going to return a pointer to an element. So what does change? Well, free changes. Right? Free changes because when we iterate over the sequence of nodes, we might have to free an element. Right? So everything's the same as before except for that one line there. Right? That's the only thing that changes. Right? So if the caller passed in a non-null pointer to a function, we're just going to use the function to deallocate the element. Right? How do you deallocate the element? Well, you call the function, right? And you pass in a pointer to the element, and that's it. Right? And so however the caller has decided that you should free the element, that function will now run. Right? Otherwise, everything's exactly the same. What about printing the stack? Right? So this line here used to be printf%d. Right? Now it's just print elem. Right? And then pass in a pointer to the element that you want to print. Right? That's a recursive version of the function of print if you want to look at that. Right? Okay, so what do these functions print elem and free elem look like, right? Well, let's see. Oh, wait, it's 20 after the hour. So I guess I have to stop there. So I guess at the very beginning of the next class, we'll look at what these functions look like. You now have everything you need to know to finish off the current assignment.